Next, I'd like us to consider equations that relate phase change. And in particular, we're talking about vapor pressure curves. So if you'll recall, back when we first started talking about pure substances, we said that if we took a graph of pressure versus temperature for a simple substance, we have a solid region, a liquid region, and a vapor region. And this curve that extends between the triple point, where these three two-phase regions come together, and the critical point, the highest temperature and pressure where liquid and vapor can coexist, in between here is the vapor pressure curve. This curve here, remember, we're going from liquid to vapor, or to solid, excuse me. So this is a fusion curve, and this curve that ends at the triple point is the difference between solid and vapor. So this is a sublimation curve. We're now going to just describe this one, although all of these can be described in similar ways. The Clapeyron equation is a theoretical explanation of what's happening along here, along this curve. And it says that pressure changes with temperature along that curve as the change in enthalpy from one phase to the other, divided by the temperature it occurs at and the difference in the specific volume from one phase to another. So if you'll recall, if you look at T versus V, the volume change for a particular temperature is going to be the difference between our saturated liquid and saturated vapor. It's the length of this curve in the saturated dome. If I were to look at a graph of T versus H, I would have a very similar sort of thing, which is this enthalpy of vaporization up here. But I select a temperature and can use this to relate to the pressure at that point. Now, people have used this in very many ways, but a very common simplification that allows us to develop a useful equation is to assume that the vapor phase is an ideal gas. And if the vapor is an ideal gas, then I can describe Vg as P over RT, or, well, excuse me, V is RT over P. And the volume of the gas, as we saw in our work in all of the first portion of thermodynamics, and we can see on the graph, the volume of the vapor phase is much larger than the volume of the liquid. So making those two simplifications, I am able to actually separate and integrate and solve for the pressure at saturation pressure, or the vapor pressure, as a function of temperature for some constant B. So if I know the value of the vapor pressure at one point, I would be able to determine all of the others. And this equation, the Clausius-Clapeyron equation, is the basis for almost every approximation method people use for solving vapor pressure as an equation. Now, the most common form that you're going to find data is going to be the Antoine equation. The Antoine equation, because it is so old, it is going to be a log base 10 of the vapor pressure is a constant minus a different constant over T plus C. Now, these constants were determined by fitting data, so it's an empirical equation. But this has been established for such a long period of time, it's so well used, that you can find the constants for this many, many places. And in fact, typically if I go on, say, Wikipedia or the NIST website, then I'm able to find these constants A, B, and C and approximate the vapor pressure as a function of temperature very easily.